So the question number 5, we have distinguish between parametric versus non-parametric models and supervised versus unsupervised learning with examples. Parametric models assume a fixed functional form with a finite number of parameters. Example, linear regression, where parameters theta is equal to WB are learned. Pros: simple, fast to train, require less data if model is correct, easy to interrupt. Cons: may underfit if true relationship is complex, limited flexibility. Non-parametric models: no fixed parameter count, model complexity can grow with data. Examples: k nearest neighbors, decision trees, random forest, SVM with RBF kernel. Pros: flexible, can fit complex patterns. Cons: need more data, may overfit, slower prediction. Supervised learning. Training data includes inputs x and output labels y. Goal: learning mapping function from x to y. Types: classification, y is categorical, spam not spam, disease no disease, regression, y is continuous. House price prediction. Example: training set of image label pairs to classify handwritten digits. Unsupervised learning. Only inputs x and no labels. Goal: discover structure clusters, lower dimensional manifolds. Examples: K means clustering, grouping customers based on behavior. PCA for dimensionality reduction. Output is patterns, not explicit labels. Relationship. Parametric or non parametric models can be used in supervised or unsupervised settings. So the second part of the fifth question is define accuracy, precision, recall, F1 score and illustrate their computation using a confusion matrix. Confusion matrix: predictive positive, predicted negative, actual positive, actual negative, TP, FN, FP, TN. Definitions: true positive, correctly predicted positives. FP, predicted positive but actually negative. FN, predicted negative but actually positive. TN, correctly predicted negatives. Matrix: accuracy is equal to TP plus TN upon TP plus FP plus FN plus TN. Precision: positive predictive value. Precision is equal to TP upon TP plus FP. Recall: sensitivity, true positive rate. Recall is equal to TP is equal TP upon TP plus FN. F1 score: harmonic mean of precision and recall to keep them balanced. F1 is equal to 2 into precision into recall upon precision plus recall. Example: suppose TP is equal to 50, FP is equal to 10, FN is equal to 5, TN is equal to 35. So total is 100. Accuracy will be the 50 plus 35 upon 100, that is 0.85, and the precision will be 50 upon 60, that is 0.833. Recall will be 0.909. F1 score will be 0.87. Interpretation: high precision gives few false positives, high recall gives few false negatives. F1 balances both, useful when classes are imbalanced. Sixth question is describe how the coefficients in linear regression are estimated using either the closed form equation or gradient descent. Solution: linear regression model where and matrix objective minimize mean squared error. This gives best linear unbiased estimator. Gradient descent iterative method. Initialize theta, weights and bias randomly or with zeros. Repeat until convergence, where alpha is learning rate. Gradient of cost function is given. Update rule, component wise comparison. Closed form, single matrix inversion, simple but expensive for very large D. Gradient descent, scales to large datasets and features. Requires choice of learning rate and iterations. The second part of question number 6 is explain logistic regression and use the logistic function to calculate the probability of a class for a given input. Example: logistic regression used for binary classification. We model probability that y is equal to 1 given features x. Linear score, logistic sigmoid function, predicted probability, decision rule, else predicted class 0. Training, maximize likelihood of observed labels or minimize cross entropy loss. Example: probability calculation. Suppose we have two features. Parameters learned from data and compute linear score z. So the z is 0.05. Compute probability using logistic function, which is 0.512. Interpretation: model is slightly more confident for class 1. Question number 7, part A. Write k-means clustering algorithm. Discuss how initial centroids influence results. Solution: k-means clustering algorithm. Input: dataset x is equal to x1 to xn, number of clusters k. Goal: partition data into k clusters c1 to ck such that within cluster sum of squares is minimized. Objective function: where mu k is centroid for cluster ck. Basic steps: initialize k centroids mu1 to mu k randomly or using k means plus plus. Assignment steps: for each xi assign to nearest centroid. Update step: for each cluster ck recompute centroid. Repeat 2 3 until convergence. Step 2 and 3 until convergence. Centroids stop changing or max iterations reached. If influence of initial centroids, k-means can converge to local minima of objective j. Different random initializations can lead to different final clusters. Problems with poor initial centroids: bad clustering quality, low convergence, high unbalanced clusters. Example: if two initial centroids start very close together, they may capture same region of data, leaving another region poorly represented. Run k-means multiple times with different random initializations. Use k-means plus plus initialization. Choose first centroid at random. For each subsequent centroid, choose a point with probability proportional to its squares. Scale features before clustering, normalization or standardization. The second part of question number 7 is write the k nearest numbers KNN algorithm using Euclidean distance. K nearest neighbors classification. Lazy instance based learning algorithm. No explicit training phase. Explicit except storing data. Euclidean distance. For 2 points, p is equal to p1 to pd, q is equal to q1 to qd. Input: training set d is equal to xi comma yi. I is equal to 1 to n with yi class labels. Number of neighbors k. For each query point q, compute distance to all training points using Euclidean distance. KNN algorithms continued. Sort training points by increasing distance. Select k closest neighbors. Set of k training points with smallest distances. Majority voting. For classification, y is equal to most frequent label among yi or for xi. For regression, y is equal to average of y. Suppose k is equal to 3 and distances from q to nearest points are votes. Predict class A nodes. Features must be on similar scale. Normalization: small k gives sensitive to noise, large k gives smoother decision boundary. Question number 8, part A. Compare decision trees, random forest and boosting, highlighting strengths and weaknesses of each. Solution: decision trees. Model: tree structure where internal nodes are tests on features, leaves are predictions. Training: greedy splitting using criteria like Gini index, entropy or variance reduction. Strengths: highly interpretable, handles numerical and categorical features, requires little processing. Weakness: high variance, prone to overfitting, small changes in data can cause large changes in true structure. Question number 8, Random forest bagging of trees. Ensemble of many decision trees built on bootstrapped sample of data. Randomness. Each tree gets a random subset of training data. At each split, consider random subset of features. Strengths reduces variance compared to single tree. Robust to noise, generally high accuracy. Can handle large feature sets. Weaknesses less interpretable, larger model, more memory and computation. Strengths boosting strengths, very smooth, very strong productive predictive performance on tabular data, can model complex linear relationships. Weakness sensitive to noise and outliers, many hyperparameters, risk of overfitting is not regularized. Question number 8, part B. Explain the architecture of components of Hadoop or describe Spark and its advantage over MapReduce. Hadoop system, batch producing framework, HDFS, master name node, stores metadata, workers data nodes, store actual blocks of data on local disks. Files are split into fixed size blocks, provides fault tolerance and high throughput. Yarn, cluster resource management layer, components, resource manager, global manager of cluster resources, node manager runs on each node, reports resources, launches containers, schedules applications and allocates CPU plus memory. MapReduce framework, programming model for large scale batch processing. Two main user defined functions: map, list of key pairs, reduce, aggregated result for each key. Execution, input data split into chunks, shuffle and sort, reduce tasks, aggregate values and write final output back to HDFS. Advantages, scales to every large datasets on commodity hardware. Fault tolerant. Spark versus MapReduce. Spark keeps data in memory, RDDs data frames, faster for iterative algorithms, supports SQL, streaming MATLAB, graphics in one engine, reduces disk input output compared to classic MapReduce, leading to major speedups. Question number A. Question number 9th, part A. Obtain basic logic gates from neural networks, summarize them in table with number of neurons, activation functions and backpropagation in neural networks. Perceptron as logic gate. Basic until neuron with inputs, weights, bias, activation F. Activation function. For logic gates often use step function or sigmoid for smooth output and gate using single neuron in choose weights and biases. Cases 0001 1011. OR gate using single neuron. Weight 1 is equal to 1, 2 is equal to 1, B is equal to bias is equal to minus 0.5. So Z will be x1 plus x2 minus 0.5. At least one input 1 gives Z is greater than 0. So the y is equal to 1. NOT gate using single neuron. Single input x, choose w is equal to minus 1, b is equal to 0.5, z is equal to minus x plus 0.5, x is 0 which gives z is equal to 0.5 is greater than 0 and so y is equal to 1 and x is equal to 1 gives 0, z is equal to 0.5 minus 0.5 is less than 0 so y is equal to 0. XOR gate needs multi-layer network. XOR is not linearly separable, requires at least one hidden layer with more than two neurons. Non-linear activation sigmoid weights are usually learned using back-propagated algorithms, and this is the given summary table. The second part of question number B, question number 9th is compare CNNs, RNNs, GANs and transfer learning in terms of architecture and applications. CNN architecture, convolution layers, filters, kernels, sliding over input, non-linear activations, pooling layers for downsampling, fully connected layers at end for classification. Key idea, perimeter sharing and local connectivity, good at capturing spatial patterns. Applications, image classification, object detection, face recognition, changing, RNN, recurrent neural network. Architecture, Neurons with recurrent connections, hidden state HT depends on input XT and previous state. Variants LSTM GRU solve vanishing gradient issues. Applications sequence modeling, language modeling, machine translation, speech recognition, etc. And then we have GAN, Generative Adversarial Network. Architecture. Generator G is takes random noise Z and outputs fake sample GZ. Discriminator D receives real or fake data and inputs probability of being real. Training. Minimax game G tries to fool D, D tries to distinguish. Applications, image generation, style transfer, super resolution, data augmentation, transfer learning. Transfer learning has idea of use a model pre-trained on a large data set and adapt it to a new but related task. Architecture. Freeze lower layers of a deep network, replace or fine-tune top layers or new dataset. Applications are tasks with small labeled datasets. Benefits save training time and computational cost, often improves accuracy when data is limited. Comparison CNN spatial data, RNN sequential data, GN generative modeling, transfer learning gives strategy to reuse existing models. Thank you.